Hello everyone, welcome to Intro to Electronics. For the next 3 weeks, we're going to be going through the basics of circuits, how to make a circuit, how to code microcontrollers, specifically Arduinos, how to then take that code from Arduino into an actual microcontroller, an ATtiny, and how to solder it onto a PCB board that we're going to mill for you guys to be able to solder onto, and make yourself your own little project to keep. So going through, we're going to start off from the very fundamentals, and we're going to go forward step by step. For the first week, we're going to really focus on what is circuits, what are electronics, basic units, stuff like that. Many of you who have taken Intro to Physics before, a lot of this is going to be heavy review. Second week, we're going to jump straight into Tinkercad. We're going to be learning how to use a breadboard, what resistors to use for different LEDs, stuff like this, and how to code an Arduino. For anyone who has any coding experience in C in the past, Arduino is C-based, so it'll be very familiar to you guys. And then finally, in the third week, we're going to do some more advanced stuff in Tinkercad, and you guys will go in and actually solder your own microcontrollers to your own boards. So, let's get started. And let's start off with the fundamentals. SI units. This is very fundamentals of not even electronics, but just of any STEM field in general. There are 7 fundamental SI units. Meters, which is for length, kilogram for mass, second for time, ampere for current, Kelvin for temperature, mole for the amount of molecule candela for luminescence. And based off these 7 SI units, we were capable of deriving a whole bunch of other units. Some of these might be familiar to you guys. For example, force, which is newtons, which is really kilograms per meter squared, all from this 7 SI units. Joules, which is newton meters, or kilogram meter squared per second squared, and so forth. In front of each of these units, either derived or foundational unit, we can put a prefix. These prefixes tell us what factor of this unit we have. For example, if I was to give in 1 meter, if I wanted 1/10 of a meter, we would have a decimeter, as that is 10 to the negative 1, or 1/10 of a meter. Centimeter would be 1/100th, and so forth. Millimeter, 1/1000th. There's the other direction we could go to. Imagine I wanted 10 meters. Well, that's a decameter. 100 meters, hectometers, 1,000 meters, kilometers, or kilometer. Following that, let's go through over the units that we actually use in electricity. So, the 3 fundamental units to really be concerned about are voltage, current, and resistance. And I'm going to go ahead and explain this to you guys in terms of water. So, forget about electronics entirely, forget about electricity, and just think about water flowing. In this situation, the first one right over here, we're going to have a big basin of water up here, and no water down here at first. Well, that water is going to want to go to the spot with no water. This water has a lot of potential energy stored up. It's high up. There's no water down here. It's going to want to flow down here. Next up, current. We're going to look at the current of water, which is just going to be, hey, there's a big tube for the water to flow through. Well, a lot of water is going to flow through. There's going to be more flow of water. A smaller tube, well, that's less flow of water. Finally, what if I were to pinch the tube in some way? Well, then I'm going to resist the flow of water. Here there'll be less resistance. Here there's more resistance. Exactly the same ideas going to come right back in electricity. If you just replace water with charge, well, in this case, if there's a lot of charge built up over here, and there's no charge down here, the charge is going to want to flow from the area of a lot of charge to no charge. This is potential electric energy, since there's a spot with a lot of charge and a spot with no charge. And voltage represents the difference in potential energy between these spots. Remember this, voltage is a difference between the potential energy stored up in 2 different areas. There is a lot more potential energy here than down here. So, the voltage is going to be high. Next up, amperage. Well, that's just the flow of charge. That's just how fast your charge is flowing. And resistance is simply something that is resisting the charge from flowing. Going from here, next example. Oh, I want to skip through here. Let's go through each of these one by one. We're going to start off with voltage. Let's go a bit more depth into them. Voltage, represented by the symbol V. Its derived unit is volts, but if you want to use it in your SI units, it would be kilogram meter squared second negative third amperes to the negative first. No one cares about that really that much. And what it does, as I was explaining, it represents difference in electric potential energy between two spots. It represents how much that charge wants to flow from one location to another location. You can put this in terms of more unit-wise, and it will be the energy, the potential energy per charge, or the joules per coulomb. And this is the idea of what is the difference of the potential energy of charge stored in one area versus charge stored in another area. Amperage, symbol we're going to use I. Its SI unit is the amps, and it represents the flow rate of charge, or just how fast the charge is flowing. And its unit is just charge per unit time, or coulomb per second. So over one spot, how much charge goes by it per second. Finally, resistance, represented with the symbol ohm or R. Its unit is the ohms. Here is its SI unit. And it shows how much the charge is getting impeded in some way. And straight up, we're just going to give you, there's a wonderful relation between voltage, current, and resistance in what's known as Ohm's law. Ohm's law is simply voltage is equal to current times resistance, or current equals voltage divided by resistance, or resistance equals voltage divided by current. Here is nice triangle images to try to help you memorize the equation if you have difficulty. Voltage on top, current and resistance on the bottom. You could solve it from there, being like, oh, current is equal to voltage divided by resistance, voltage equals current times resistance, current equals voltage divided by resistance. But really, if you just memorize voltage equals current times resistance, you'll be good to go. You can derive the rest. The next thing we're going to discuss is power. You guys probably heard this a lot. I had a big electricity bill last month. I pay it because I used a lot of power. What is power? Well, power just represents the amount of energy spent per unit time, or joules per second. And we can figure this out. We can calculate joules per second through these different relations. Right here, we can see that power is going to be equal to resistance times current squared, or current times volts, or volts squared divided by resistance. And here's all of the other relations that includes power within. So if you're given if you're given 3 bits of information, you can solve for the 4th at any time. And actually, if you're given 2 bits of information, you could solve for any of the other 2 at any time. Not even. There we go. So let's go through and actually cover some circuits. So we're going to start off by discussing what's an open versus a closed circuit. As we discussed, voltage is the difference in potential energy between 2 points, or how much a charge wants to flow. Well, if we look at a battery we always see is given some sort of voltage. Here I'm giving you a 10-volt battery. Well, that means between this point up here and this point down here, there is a difference in electric potential energy of 10 volts. That means the charge wants to go from this point all the way around to that point. However, in this circuit over here, we can see that there is this gap here. Well, that means that all of this here is charged with the same 10 volts. Since there is no spot with less electric potential energy, this charge doesn't actually want to flow somewhere. So if I were to go from this point to this point and check the voltage, the difference in electric potential energy stored in the 2 parts, it would be 0 volts, simply because the whole thing has the same electric potential energy. It's not connected to a spot with no electric potential energy. You also saw that I threw a resistor in here. Well, imagine there was no resistor. Well, we could use Ohm's law to calculate the current. If there is a resistor, we could say voltage is equal to current times resistance. Calculate the current, so therefore voltage equals current times resistance. Current is equal to voltage divided by resistance. Voltage is 10 divided by 100 is 0.1, so this would have a current of 0.1. Well, what if we get in a situation where there is no resistance? There's a 0 ohm resistor. Well, or no resistor, matter of fact. Well, in that case, you're going to end up in a situation where you're actually going to get something divided by 0. Current is going to be 10 volts divided by 0. That doesn't make sense. You cannot divide a value by 0 for any of you who have taken a math course at all. And for that reason, there has to be some resistance, or else it's going to just go into infinity. And this is actually a problem that occurs in real life, which will be called a short circuit. If you don't have any resistance in just a wire connecting 2 points, or not enough resistance, it's going to have a lot of excess energy, and what's going to happen is going to generate into heat. And you don't want that, so make sure that you use your resistors, or else stuff will turn very hot and explode. Next up, we're going to actually go ahead and work on this resistor and apply Ohm's law to it. Imagine I give you this resistor, as I previously discussed, 10 volts, 100 ohm resistor. Want to calculate current, as previously stated. Voltage equals current times resistance. Current is equal to voltage divided by resistance. 10 divided by 100 is 0.1, or 100 milliamps. Remember, milli is a thousandth of an amp. So 1,000 milliamps is 1 amp. So 100 milliamps is 0.1 amps. Now, I want to point out this tool. This tool is called an ammeter. An ammeter will tell you the amp, or the current, as charge flows through it. The charge will be flowing through this, and it could tell you this. Remember, an ammeter, unlike voltage, isn't the difference between 2 points. It is simply the flow at a single point. Let's go to the next example. Let's try to solve for voltage. Well, we have the ammeter. It tells us the current, 0.5 amps. And we have a resistor of 24 ohms. Voltage equals current times resistance. Voltage is equal to 0.5 times 24. Voltage is equal to 12 volts. There you go. Now, there's something we could use to have seen this. If we were lacking information, we could have used what's known as a voltmeter, which is represented by this unit over here, this symbol over here. And remember, the ammeter shows flow going through a single point. Voltage is the difference in potential energy between 2 points. So, it needs to be connected on 2 different sides of the batteries in order to show the difference in potential energy. And as you can see, it gets us 12 volts. So, let's go on to a bit more complex circuits. We're going to learn about series circuits. A series circuit is when we have multiple resistors in series to one another. And one of the big questions you're going to want to ask yourself is, what is the total resistance of this series, of the series circuits? Well, easily enough, you could solve that. Total resistance of a series circuit is just going to be adding them all together. It's also called the R equivalent, or the equivalent resistance, since it's the equivalent resistance of all these resistors put together. If we go ahead and we add them together, 10 ohms plus 20 ohms, it makes 30 ohms. The total voltage of our system is going to be 3 volts. However, that's between the first point and the last point, both terminals of the battery. However, when we're looking at, whenever something undergoes a resistor, there's what's known as a voltage drop. So, and what that means is the voltage between, so if we were to look at the voltage and we were to compare it between this point and this point, we would see the difference in electric potential energy across this resistor. If we were to go back to our previous example, we saw that the difference in electric potential energy across this resistor over here was in fact 12 volts. In this case, we're going to see something similar. We're going to see that there is a difference in electric potential energy between this resistor and between these. However, between both of these is going to be 3 volts. Now, how do we solve this? Well, first of all, we're going to need the current of the system. And the current, unlike the voltage, is going to remain consistent throughout the entire circuit. And the reason for this, if you picture this, is charge wants to be spaced out evenly, sort of like traffic. Therefore, it's not possible for more charge to be leaving the battery than is coming in at the other end. If there was, imagine if you had charge going really fast over here and slowed down here, there would be a blockage here. But as I said, charge wants to separate. It's like traffic. Well, that means it had to slow down here, and slow down back at this portion. So at the end of the day, current throughout the entire circuit that's in series is going to be equal. Alright, so we can solve for the current of the circuit. We have the total, which is 3 volts. The total resistance is 30 ohms. Well, that means voltage divided by resistance, or 30 divided by 3, is going to be equal to 0.1. Oh, sorry about that. Voltage equals current times resistance. Voltage is equal to current times resistance. Voltage divided by resistance. So voltage is going to be 3. 3 divided by 30 is going to be 0.1 amps. Sorry, double checking my math. Thought I made a quick error there. So now with this information, we know the current of the system, and we know its total resistance and its voltage. Well, we can now figure out the voltage drop across each resistor. So we want to solve the voltage. We have the current. The current is equal to 0.1. And the resistor is 10 ohms. Well, voltage equals current times resistance. That means the voltage drop across this resistor, or R1, the first resistor, is 10 times 0.1, which is 1 volt. We can do the same thing for this one. Voltage is equal to current times resistance. Voltage is equal to 3. Voltage is going to be equal to the amount of volts going from here to here. Well, we want to solve for that. Current is going to be equal to 0.1. Resistance is 20. 0.1 times 20 is 2 volts. That means the voltage drop across the first resistor is 1 volt. So between this point and this point, we would see 2 volts, since 3 minus 1. And then the voltage drop against this resistor is 2 volts. So from this point to this point, we would see 2 volt different. Therefore, if we go from here to here, it's going to be 3 volts, which is 1 volt plus 2 volts. Next up, we're going to learn about parallel circuits. Parallel circuits are simply circuits where there are multiple paths that the charge can take. In this case, we see that there are 3 paths the charge can go down. It can go down the first path, the second path, or the third path. Well, to solve for the total resistance, just as we did on the last one, it's actually going to be equal to 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3 and so forth, where R1, R2, and so forth are just the values of your resistors. Interestingly enough, if you did a calculation, it is 5.71 ohms. Well, you would realize that's less than the resistance of any single one of these resistors. And that makes sense, because what's happening here is the charge is going to be traveled, and it's going to travel through the path with the least resistance. Well, it's going to first travel here, 10 ohms, convenient, lowest resistance. The charge right behind it, though, will be like, oh, there's someone here right now. This is occupied. Well, let me go down the path of 20 ohms. Same thing for the third one. The first 2 are filled. Let me go down the path of 40 ohms. As a result, there are more paths where to take. So you're going to get a total resistance that is going to be less than your lowest resistor, since there is at least more options than that one to take. They might be slower, but they are still present. The voltage between here and here is, however, still going to be 10 volts. The voltage drop across each one of these resistors is going to end up being all the same, and they will all be 10 volts, and we could prove that. But what is interesting, though, as I was mentioning, because these are each different resistors going down different paths, the current is no longer the same. Charge can be flowing faster through R1 than it is R2 or R3, and it can all, but as long as the total current that leaves this terminal is the same amount of current coming into this terminal, that means we followed all the rules we has previously established. So let's try to figure this out. We have the voltage, which is 10 volts. We have the current, which is 1.70. We have the resistance, which is 5.71. Voltage is equal to current times resistance. Solve for current. Current is going to be equal to 1.75 amps. Now, as discussed, along each path, current is going to change. Let's figure out the current for each individual path. Well, voltage is equal to current times resistance for this one. That means that current is going to be equal to voltage divided by resistance. So voltage divided by 10, 10 divided by 10 is 1. So along this path is going to be 1 amp. Same thing for here. 10 divided by 20, okay, you remember, current is equal to voltage divided by resistance. That's going to be half an amp. Last one here, 10 divided by 40. Well, that's 0.25 amps. We can see it all right here. And now, if we add them together, 1 amp plus 0.5 plus 0.25 amps, it brings us back to our total current of 1.75 amps. Therefore, the amount of the flow of the charge exiting this terminal of the battery and coming into the other terminal of the battery is the same. We can also calculate the voltage drop across each resistor to show that they are in fact the same. We have the current along each path. Well, that means voltage is equal to current times resistance. Voltage is going to be, for this one, 1 times 10, which is 10. 10 volts dropped across this resistor. 0.5 times 20, which is 10. And 0.25 times 40, which is still 10, as shown here. So the change in current electric potential energy between this point and this point across all the resistors is going to still be 10 volts. Next up, we're going to move on and we're going to learn about simplifying more complex circuits. We're going to use this information we previously learned to take a more complex circuit that has both series and parallel connections and make it into something more manageable. So here's our example problem. It looks pretty daunting at first, but it's perfectly possible. Imagine I were to give you the simple question that will be on the homework: find me the total resistance for this circuit. Well, let's start off by breaking down what we can see. The first thing I see, obviously, is there is a series circuit. There's a series resistors here and series resistors here. Well, let me add these together to make 30. These together to make 35. Nice. So we're cleaning it up a bit. Let's keep going. I see 3 parallel resistors here. I see there's a path going from here and a path from here. And here they got 3 paths to choose from. Perfect. Let's use the equation we learned. And we can clean it up a bit. Bam. Okay. Now we're down to just 3 resistors in series. Add the 3 together to make 57.78. And there we go. Now you've found the total resistance of that circuit. That being said, these problems aren't the easiest for people to get. This PowerPoint video might have taught you absolutely nothing. It might have taught you a ton. In any case, out of anything we've learned so far in this entire class, this is by far the easiest one to go online and search up. There's plenty of resources available from Khan Academy, Organic Chemistry Tutor, Spark Academy, DigiKey, tons of resources if you're wondering how to solve this. Any Intro to Physics textbook will have stuff. Intro to Electronics, Intro to Circuits. In addition to that, over the next 3 weeks, I will be hosting office hours. Every Tuesday, Thursday, and Friday, there will be a sign-up sheet that isn't mandatory to sign up to. You could still walk in freely, but if someone else has an appointment, they will have priority. But regardless, if there's a second and I'm free, I will help you guys out. Just come in. It'll be at the WinHub. And I can help you guys explain a bit more. There's a problem set due for this week. It's going to be very standard circuit type problems, nothing special. You could probably Google these problems online to get a general idea of what you're solving for, which is why you need to show your work. If you manage to find the answers online, good for you. Just make sure you show your work, make sure you understand it. Because here's the thing, if you don't understand it now, when it comes next week, I'm not going to spend any time slowing down to explain these topics. I'm going to just be simply throwing out the words voltage, current, resistance, we want to balance them, and so forth, blah, blah, blah. And I'm not going to slow down at all. So it's very important you guys have a firm grasp on these fundamental topics. So from here, we could really move on and worry on the actual meat and bones of circuits. Well, good luck to all of you guys on the problem set. See you guys during office hours. Good luck.